Hello, everyone. I have had a few requests to provide a little more information on standard cell potentials and calculating those for cells. Before I get into this video, I apologize for the sound quality. There's a lot of echo with this sound right now. I don't have my regular microphone. And so once again, I apologize for the quality of the sound, but I wanted to get this video out here as quickly as possible today. What I have on the screen right now is a table of standard reduction potentials. I've posted this in Brightspace, and I've linked to it in the redox reaction lesson as well. This table here shows the amount of energy produced or required in common reduction reactions. If you take a look at all of the forward reactions, we see that they all involve gaining electrons. So those are reduction reactions. If we reverse the reaction, those would all be oxidation reactions, the loss of electrons. When we read this table, we are always reading it in the forward reaction, and that links to the energy value here. Positive reduction potentials indicate energy is produced in this specific reaction. These energy values are not absolute values. If I scroll down here, I see one value in red, and that's the reduction of hydrogen ions to form hydrogen gas. Since an electrochemical cell or a redox reaction must involve the gain and loss of electrons, the energy produced depends on both half cells. Chemists have set this specific reduction reaction to be 0. All of the other energy values are based upon how much energy would be produced or how much energy would be required if the hydrogen reaction I'm highlighting right now was paired with another reaction. So for example, if in one half cell, copper 2+ ions were reduced to form copper 1+ ions, and in the other half cell, it was the hydrogen reaction in red, the difference between those two would be 0.16 volts. That's how much energy would be produced. We'll come back to comparing those energy values in a second. This table is organized from reduction reactions which involve a very strong oxidizing agent, so elements or ions which have an incredible attraction for electrons at the top, and then at the bottom of the table, we have the elements or ions which have the weakest attraction for electrons. So not surprisingly, we see elements like fluorine, we see molecules like hydrogen peroxide, the permanganate ion. These elements here all have very strong attraction for electrons, and as a result, when they gain electrons, they produce a relative high amount of energy. I'd like to go through an example of calculating cell potential. Just note that the values that I'm getting for the reduction potentials in my example question come directly from this table. Okay, that's where I'm getting these numeric values from. Let's go and look at that now. Here's the question we'll look at. This is similar to the questions that are in the redox lesson in Brightspace. Determine the standard cell potential for an electrochemical cell that is constructed using the electrons that are based upon these half reactions. So when half reactions are listed out, they're commonly just listed all as reduction reactions. Okay? The reason for that is whether a reaction is going to be an oxidation or a reduction depends entirely on what that specific reaction is paired with. So in order to standardize everything, we just always list things as reduction reactions and then determine based upon the energy values here, which direction the reaction will go in. So my first step here is to determine which of these two half cells is going to be the oxidation and which one's going to be the reduction. I'm going to look at the two reduction potentials to decide. The gold reaction here has a reduction potential of plus 1.5 volts. So that means it's releasing energy. The lead reaction is negative 0.13 volts. That means energy has to be put in. So comparing these two, gold is a much stronger oxidizing agent than lead. So if these two reactions would be paired, gold would pull the gold ions would pull the electrons towards it from the lead. So that means we need to reverse the lead reaction. So let's do that now. I've reversed the first reaction, and now I've got my two half cells. The gold reaction up top here is the reduction, a gain of electrons. And the lead reaction, which I rewrote and reversed from the original, is the oxidation. Because I reversed the direction of the reaction, I've also reversed the energy value. If the reduction potential requires 0.13 volts, then the oxidation reaction is going to produce 0.13 volts. In the content section of Brightspace, they ask you to balance the electrons gained and lost. If we're just trying to find the cell potential, that doesn't matter, so I'm not going to right now. The cell potential is going to be equal to the reduction potential plus the oxidation potential. 1.50 volts plus 0.13 volts Let's review my steps. I'm given two half cell reactions and I compare their reduction potentials. The reaction with the lower or more negative reduction potential is going to be the oxidation reaction. I reversed the reaction which had the lower or more negative reduction potential and rewrote it and flipped the sign on its potential as well to make it an oxidation potential. To find the standard cell potential, I summed the reduction potential and the oxidation potential to get my standard cell potential. So in this reaction here, 1.63 volts would be produced.